Hi, we are going to talk about the Deutsch algorithm. And the setup is the following. You have a function f from 0, 1 to 0, 1. And you have the right to query the function. So you can query the function or call the function. And the goal is to find out if the function is constant or not. So by using the minimum number of queries. So find if the function is constant or not. So what are the possibilities? So if I draw the function in this way, so I have 0, 1, and this function is a function from 0, 1 to 0, 1. So a constant function would be something like this. So the 0 goes to 0 and 1 goes to also 0. So this is one possibility. So this is constant. Or we could have both 0 and 1 go to 1. So this is another way that the function could be constant. And of course, there are two other possibilities. And well, it could be 1-to-1 in this fashion, or it could be this possibility. And we'll call these cases as balanced. So the function could be either constant or balanced. And by making a minimum number of queries or calls to the function, we have to determine if the function is constant or balanced. Now, classically, you can query the function by making a function call. In the quantum sense, if you have to build such a circuit, we have to make a unitary operator. And querying in the quantum sense is essentially calling this black box. The black box looks like this. So what is querying in the quantum sense? Well, it is to call a unitary operator that we are able to somehow determine the value of the function at that point. So let me just draw a unitary operator for this type of function. So you have a black box. Let me call this U of f. And its inputs are x and y, and outputs are x and y XOR f of x. Right? So using this black box, you can query the function. And calling this black box once would be calling this function once. And let's see how we can utilize this. And so the black box itself will be different for different functions. So each of these 4 functions will require us to implement a different U of f. But we are not really worried about the implementation details, since we are only concerned about what the function returns. The details are not as important. So here is a proposition. if I apply u of f to x tensor 0 minus 1 over square root 2, so the top qubit has some value x, which can be either 0 or 1, then it returns minus 1 to the f of x tensor 0 minus 1 over square root of 2. And in a sense that we get an idea whether f of x is 0 or 1. If f of x is 0, then we'll get this same output as the input. If f of x is 1, then sort of mark by phase, a global phase, which is minus 1. So let's try to prove this. So let's see what happens when, so proof, right? So u of f, so since u of f is a unitary operator, and particularly it is a linear operator, so u of f of x tensor 0 minus 1 over square root of 2 will be equal to u of f x 0 minus u of f x1. So this is due to linearity. Then we have the action of u of f here on the screen. So this will be u of f, sorry, this will be x, and this will be f of x XOR 0 minus x f of x XOR 1 over square root of 2. Right? So this is going to be x f of x minus f of x bar, which is the sort of the inverse or the invert of the f of x. Right? So now if f of x is 0, then you will get, if f of x is equal to 0, then this answer will just be x tensor 0 minus 1 over square root of 2. However, if f of x is 1, then this will be x tensor 1 minus 0 over square root of 2, which is equal to minus 1 to the 1 into x tensor 0 minus 1 over square root of 2. Therefore, the action of u of f x tensor 0 minus 1 over square root of 2 will be equal to minus 1 to the f of x tensor 0 minus 1 over square root of 2. So that is the proof of this proposition. So we'll be making use of this black box or query function in our circuit to solve the Deutsch problem. Let's see what the circuit looks like. So the Deutsch circuit looks like the following. Let's draw the circuit. So Deutsch circuit. We have a Hadamard gate. Then we have this u of f. This is our query function. We have one more Hadamard gate over here. And then we have a measurement. All right. And this is going to be get 0. This is going to be get 0 minus 1 over square root of 2. And I claim that over here, you will get the answer whether the function f is constant or balanced. So let's analyze this circuit. Let's look at various time points where, so we have going to analyze the circuit at various points. And let me call these psi 0, psi 1, psi 2, and psi 3. Okay, so it's clear that psi 0 is just 0 tensor 0 minus 1 over square root of 2. And then you have the Hadamard gate. So the first qubit 0 goes to 0 plus 1 over square root of 2. So psi 1 will be ket 0 plus ket 1 over square root of 2 tensor 0 minus 1 over square root of 2. And I'm just going to write this a little differently. This is going to be 0 tensor 0 minus 1 over square root of 2 plus 1 tensor 0 minus 1 over square root of 2. All right, so let's apply the proposition over here. So this is going to be minus 1. So this, I apologize. It will, let's look at this. So this will be psi 1. And I am now going to apply this black box. The black box takes xy and outputs x tensor y plus f of x. Sorry, y. Yeah. So now let's look at what happens when the black box query function gets applied. So this is going to be psi 2 will be equal to minus 1 to the f of 0, 0 tensor 0 minus 1 over square root of 2 plus minus 1 to the f of 1, 1 tensor 0 minus 1 over square root of 2. All right. So let me rewrite psi 2 as minus 1 to the f of 0, 0 plus minus 1 to the f of 1, get 1 over square root of 2 tensor 0 minus 1 over square root of 2. All right, so this will be psi 2. So now let's analyze this a little bit. So there are two cases. If f of 0 is equal to f of 1, so two cases. So psi 2 will be equal to 0 plus 1 over square root of 2 plus or minus. If f of 0 is equal to f of 1 is equal to 0, it will be plus. And if f of 0 is equal to f of 1 is equal to 1, then it will be minus 1. So there will be a global phase of plus or minus 1 tensor 0 minus 1 over square root of 2 if f0 is equal to f1. Right? If f0 is equal to f1 is equal to 0, then there will be a plus sign. If f0 is equal to f1 is equal to 1, there will be a minus sign. So this is one possibility. And the second one is if f0 is not equal to f of 1, then let's consider f0 is 0 and f1 is 1, then this will be get 0 minus 1 over square root of 2, right? On the other hand, if f0 is 1 and f1 is 0, then there'll be a minus sign over here. So either case, there'll be a global phase of plus or minus 1, tensor 0 minus 1 over square root of 2. This happens if f0 not equal to f of 1. Okay, and so this, you probably now understand what's going on. So over here, we have only one more gate to apply. We are over here, and final gate to apply is the Hadamard gate. And after applying the Hadamard gate, we will be in a state psi 3. So let's write psi 3. This is post applying the final Hadamard gate. This will be plus or minus. The Hadamard gate takes 0 plus 1 over square root of 2 to 0, tensor 0 minus 1 over square root of 2. The Hadamard gates takes 0 minus 1 over square root of 2 to get 1, tensor 0 minus 1 over square root of 2. And so our final measurement, we will be able to, on the first qubit, we'll be able to distinguish if the function was constant or balanced. Because if you look at notice psi 2, this is if f0 is equal to f1, and this is if f0 not equal to f1, right? So measuring this first qubit, if I get a 0 answer, then I know the function is constant. If I get a 1 answer, the function is balanced. So the point is that we required only one call to this u of f function. And this u of f function is called an oracle or a black box. It's the equivalent of calling the function in the classical case, or writing a subroutine for the function. Either case, using this Deutsch circuit, using a quantum algorithm called the Deutsch algorithm, we are able to distinguish between these two cases only in one query or one call to the oracle. So that's the Deutsch algorithm.